Hi there. A few years ago I was working for a company and they wanted some more engineers. They offered me a permanent position, but I was only interested in contract. So I agreed to actually sit in on the interview and actually interview some of the guys that was coming in for my role. And one of the questions I came up was, to my mind, it was quite an interesting question. It was a simple circuit, and I basically asked them to solve various parameters of it. At the end of the day, we were looking for guys that could repair PCB, so obviously they had to know how the thing worked. So it was a simple circuit. At the time, the circuit was actually drawn on paper, but I'm actually going to do it on in OrCAD. Yes, I know OrCAD is an expensive tool, and not everyone has access to it, but it's a tool that I use. I basically use it for my fault finding endeavours. You'd be amazed how much information you can actually get from a schematic actually in the tool, rather than on a PDF or or even just a simple piece of paper with the schematic drawn on it. So without further ado, let's pop up OrCAD. OrCAD is an expensive program, I do agree, and as you can see here, I'm actually running at 17.4, which is the latest one. I've got a few options here, and I've bought these options over the years just to help me in my fault finding endeavours. I even use PCB to help me fault finding, so it just makes it a lot easier for me. So we're going to use Peter Spice Designer today. Once I've explained how the circuit is, we're going to use PSpice to actually solve it for us, but we don't actually need it's going to be that simple. If you know what you're talking about, you will quickly find out how this circuit works. So without further ado, let's press the OK. It takes a few seconds for it to suddenly initialize itself. So here we go. So what we do, and we're going to call it exam question. Okay, normally it's got there we go, OrCAD design files. And then we call that exam question as well, so that would actually make a directory for us. Okay, so click on OK. We want to create a blank project. You can actually, it's got some built-in projects, as you can see, but there's nothing there that we need, so we're going to create a blank project. It takes a few seconds for this to happen. And there we go. We don't need the start page, so we can either use PSpice part search, or I know where the parts are. Go into PSpice. So we want 3 resistors. We rotate them. One there, one there, one there. Click on the escape button. Now we want obviously a PSpice ground, which is quite required. That gives you node 0, and the last is obviously a voltage source. So we can use DC. Right. So now let's connect them up. So you can either go over here and hit that tool there, or you can just press wire, and as soon as you start moving the cursor, it changes to a cross. So as you can see, it's fairly quick to connect, and there we go. The next thing we want to do is to change the component value, so we're going to use 10k resistors. And this one is going to be our problem, so we're going to have a question mark because we don't know what the value is. Now the question is, at maximum power transfer into this resistor, what would be the expected voltage on this net here? So we will call it a name. Can I find it? There we go. I don't know, V out. So what would be the voltage on V out if this resistor is at maximum power has a value, so maximum power transfer takes place? So the first thing we need to know is, for maximum power transfer, this resistor value is somewhere between a short and an open. For maximum current transfer to take place through that resistor, it has to be a short. For maximum voltage transfer, it has to be an open. And obviously maximum power transfer is going to be somewhere in between. So this resistance here basically has to equal a source resistance. So this is the load resistance, this is the source resistance. Now out of the 5 people that I interviewed for this question, I think only one person got it right without any prompting. No one else got it right even with prompting. So they all worked out that for maximum power transfer to take place, the load resistor had to be the same as the source resistor, or source resistance, but they couldn't work out what the source resistance was. So what we need to do is really one thing I forgot, I haven't given it a voltage yet, so we do that and we give it 10 volts. So we need to work out what the source resistance is. Now that to happen, we basically need something like this. Let's just place these here. So this would be obviously source resistance, this would be load resistance, but at the moment we don't know what that is. And we don't know what value that is. And to be honest, we don't know what that's going to be. Okay, so basically what we need is a circuit like this. Okay, now if we isolate this resistor here, and then all we got is just R1, R2 and 10 volts, so in other words the load is open circuit. For a 10 volt power source, we will have 5 volts here. Okay, so take the load away, and having this voltage and this resistance here would be the equivalent of this circuit here. And this is what we called a Thevenin equivalent circuit. Okay, so V out, if R3 was open circuit, would obviously be 5 volts. We've got two 10k resistors there, so it's 5 volts. So let's call that 5 volt DC. Okay. Now, to find this resistance, or the Thevenin resistance, if it's a voltage source, you short circuit it. So if you short circuit this voltage source, that point is the same as that point. So basically you got R1 and R2 now in parallel. Two 10k resistors in parallel would give you 5k. So let's put 5k. This is now the source resistance. Aha! If you remember, for maximum power transfer into that resistor, it has to be equal to source resistance. So this is also 5k. This is just another way of doing it, by the way. You can click on it and the component, and well, it's the value 5k. And there you go, put 5k in there. Okay, so now we know what this is. This is now 5k. Now, if this is 5 volts and these two are 5k, this voltage here, which would be V out, is now going to be 2.5 volts. Okay, so now we worked out what resistor is. We can now work out what that voltage is at this point, 2.5 volts. So let's, we don't need that anymore. And now let's simulate this. So what we have to do first of all is set up a profile. Again, I'll call it exam question. Oh, my mistake, it doesn't like... Okay, in a few seconds we can now start doing all our various PSpice simulation profiles. At the moment, all I'm interested in is the bias point. So let's give it a bias point, and all that's going to do is generate all the various voltages around the circuit. Let's start the simulation. On the first one, it takes a bit of time to generates the PSpice net. And there we go, all the voltages and the various currents around the circuit. And yes, as we predicted, it's going to be 2.5 volts. Okay, what's the power going to be? So if I get a power dissipation and actually put it on the component we're interested, we have to do another change of simulation. So we're going to do that. We don't want bias point anymore, I'm not interested in that. So what we want is a time domain. Okay, and we're going to run it, in this case we'll leave it as a default for 1,000 nanoseconds or 1 microsecond. Can apply, hit OK, and then press that. Give it a few seconds and our simulation, and there we go. It is at roughly 1.25 watts. If we wanted to see what it was, we can click on toggle cursor, and if we click on maximum, and there you go, it comes out at 1.25 or 1.25 milliwatts. Okay, right, let's get rid of that. Now, how do we know that that is the maximum power that can be transferred into that resistor? So what we have to do now is sweep the value of R3. We believe it should be 5k, so if I sweep it from 4k to 6k, we should be okay. So before we do that, we actually need a special component. So if we search for part, sorry, in there, add library, and what we want this, it's a library called special. As you can see, I've got lots of libraries in here. There we go. And down there would be a component called theorem. There we go. So we can put that on there. What we're going to do now, we can set up a sweep or R3. So if we either double click or right click and edit properties, we're going to call it, give it a new property. We can call it what we want, but I'm going to call it RVAR, variable resistor or variable resistance. Okay, I want to display it and put a value. We believe it should be 5k, so that's the value we will put in. And what that means is if I'm using any of the simulation tools with PSpice that doesn't sweep that value, it would take the nominal value of 5k. So if we apply it, and because I said display on off, a little window will pop up and I want the name of value displayed. Okay, so now it's asking me, do I want to put another one? No, I don't. So hit cancel, close the property editor, and there we go. But at the moment we're still not ready to sweep that component. What we have to do, click on that, which is, and so it picks up our var. What we have to do is put it in curly brackets and then call it RVAR, and then okay, so now we're ready to sweep. So what we do now, we have to set up a simulation profile. We're going to use time domain, but we can use parametric sweep. Okay, we can use a global parameter. Parameter name RVAR. Okay, we can give it a start value. I said 4k, and then value 6k, and an increment. So this is how many different sweeps you want, how many different component values you want. I'm going to use 10, as in 10 ohms. So it's going to start at 4k, 4k10, 4k20, and so on and so on. Okay. We can leave it linear. I'm not really that too worried. So we can apply, press OK. Now obviously this time when we do the sweep, it's going to take a bit of time. So start this simulation. This is a probe, and you can see, there you go, it didn't take that long, and as you can see, it's got lots of graphs it's going to display. As you can see, the maximum is 1.25 milliwatts, and goes down to just below 1.235 milliwatts. Now, I obviously don't know what resistor value will denote what 1.25 milliwatts. Okay, so in this case, we have a tool we can use. So if we go into trace and use performance analysis, I actually done 201 sweeps then, so I actually ran that simulation 201 times, and that's the variable that's changing between the sections is R-bar. Well, we know that, that's what we asked for, and a range of changing variables between 4k to 6k ohms. The x-axis will be R-bar, so R-bar will be this value down here, and the y-axis depends on the measurement we use. We can, if we wanted to, actually take out some of the sections. So if we thought 201 graphs was too much, we could actually delete some sections, but we're not going to do that. So if we hit wizard, and And here we are, performance analysis wizard, step 1 of 4, blah blah blah. It just basically gives you what it is you're actually going to do. So if we click next, the first measurement we're going to do, or sorry, the only measurement we're going to do, is going to be one of these. Now, because obviously it's a DC variable, I'm not really worried, so I'm going to use max. So there's max. So we hit next. Okay, so it's already started building the equation. Name the trace to search. Now, when you do a simulation, it simulates everything in circuit, so you have to know what it is. Obviously it's R3, but if you're not sure, you can click that button and you can get all these ones. Now obviously we're interested in power, so we click WR3. It stands for watts. If you can't see watts, just make sure it's collected there. So press OK, and there you go, it's built up that equation. Now if we hit next, what this is saying, just to make sure that you picked up the right value or the right equation, it will just plot one of those graphs. In this case it's obviously taking the one right at the low end. If we're happy with this, click next, and it gives us two charts. So this is the chart of that equation we just built up, and this is the original one. We obviously don't need this, so if you click on it, then go into plots, delete plot, and now we've got this. Again, right at the top is 1.25, but you know, it's at the top of the graph. How are we not known that obviously we can't bit that graph off? So what we can do is go into plot, go into axis settings, and go into the y-axis and click user defined, and sorry, I've got a bit too wrong there, so there you go, not quite, so let's there you go. It's but again, you can only see some of the plots. If you want to zoom into that, what you can do is actually go into plot, axis settings, and you can actually control these. So at the moment it's going from 1.23 to just over 1.25. So you know, like I said, you can actually change this and just actually plot just this section here if you want, and it'll have a lot more points on the graph. We're not really interested in that. Let's have a look, see how much it is. So click on toggle cursor, and because we want the one at the maximum, it'll be the cursor max. Click that, and there you go, 1.25 at 5k. So that is our point there, and that is how you find the value of that resistor to give you maximum power transfer. Thank you for watching, and if there's anyone out there that requires me to come along, you know, to help you with some of your simulation, obviously this is a simple simulation. PSpice has got the power to do more powerful ones. You can get a PSpice from TI. It's a cut down version, and I'm not sure how many nodes it'll do. I'm guessing around about 200 nodes. This version that I got is basically unlimited. Obviously it depends on how powerful your computer is. Some simulations can take a long time to simulate, so if you need me to help you with some simulations, or even to debug some of your PCBs. You got a load of PCBs standing in the corner that's costing you money as they're not being sold. Just ask me and I'll come along and I can fix your PCBs. That's what I do for my bread and butter. But I basically use OrCAD to help me understand various circuits, and I've even got the PCB tool, and you'll be surprised what PCB tool can help me do as well. Thank you for listening. Until next time, see you later.